All right, let's talk about um, capacitors. And we're going to start our kind of introduce what a circuit diagram is, because a capacitor is an element in an electric circuit that stores charge. So a circuit diagram is pretty easy. We have some kind of voltage source like a battery, and the symbol for that could look like this or like this. And the short side is always the positive terminal, and the long side is always the negative terminal. That's the rule. Wires are just lines, and capacitors are two parallel lines. And a resistor, which we'll talk about later, is a squiggly line. So the way that a diagram is made is you have to have some kind of voltage source. So I'm going to put a battery in here. And I'm going to connect it to a capacitor. So it's important that you recognize that the battery is the one that has the long and the short, and this is the positive side, and this is the negative side. And the side that is of the capacitor, which is two parallel lines of the same length, that is connected to the positive terminal will be the positive side of the capacitor, and the side that's connected to the negative side of the terminal will be the negative side of the capacitor. Current, even though we know that current is a flow of electrons, when we first talked about circuit diagrams, we didn't know anything about electrons. So we said that electricity flowed, and electricity, you either had it or you didn't. So it was a positive flow. So our current is always going to go from positive to negative. So it would start here at the positive terminal and go around. But what we really know is that what's happening is that the electrons are flowing this way, and they're going to build up on the chart on the side of this, and that's going to induce a positive charge. And when that gets fully loaded with electrons, then this will have its full positive charge, and because there is an electric field that exists here, the electrons will flow through to the other side. All right. So what we want to do is we want to talk about what happens when we put capacitors together in different ways. So one way to put elements in a circuit is to put them in series. And that means that when you have a diagram like this, notice that this is the positive side, this is the negative side. If you can trace only one loop of current, it says that those devices are in series. So let's talk about what's happening there. So each capacitor will have its own voltage, right? If I were, and that's dependent on the area of them and the separation and their capacitance, right? So the voltage that the maximum voltage across each of these capacitors, V1, V2, and V3, should add up to be the voltage of the battery, right? The voltage of the battery. So voltage of the battery is going to be equal to the voltage of the first capacitor plus the voltage of the second capacitor plus the voltage of the third capacitor. And remember that C equals QV. So V in general is Q all over C. So if I want to know what the voltage is of capacitor 1, I would need to know what the charge is divided by capacitor 1. And the charge of divided by capacitor 2, and the charge divided by capacitor 3 would find the voltages. So all I've done here is now let's talk about why the Q is the same here. Because this battery does not know that it's connected to separate devices. It's going to think of this capacitor as one capacitor, and electrons are going to build up on this side, or build up on this side, and build up on this side and induce a positive charge on this side, which will induce a negative charge on this side, which induces a positive charge on this side, which induces a negative charge on this side, and a positive charge on that side. So really, the total charge on all of these is going to be the same. So we can say, instead of saying Q1, Q2, and Q3, we can just say Q. Q1 equals Q2 equals Q3 equals Q. They have the same charge on them. And if we pull out that common term, we'll get Q, the voltage across the battery is equal to Q times 1 over C1 plus 1 over C2 plus 1 over C3. So this term here is called the equivalent capacitance. In other words, it's as if the battery is connected to just one capacitance called CEQ. And that capacitance, 1 over CEQ equals 1 over C1 plus 1 over C2 plus 1 over C3. So let's just put some numbers in here. If C1 is 1 farad and C2 is 2 farads and C3 is 2 farads, then 1 over CEQ would be 1 over 1 plus 1 over 2 plus 1 over 2. And I could put this in my calculator, right? 1 over 1 is 1 plus 1 over 2 is 0.5 plus 1 over 2 is 0.5 equals 2. If I want to find CEQ, then I'm going to need to take the inverse of both of these. So CEQ would be the inverse of 2, or 1 over 2, or 0.5 farads. So this battery is attached to a 0.5 equivalent capacitor. The more capacitors that are in series, the less the equivalent capacitance. So that means that it can hold less and less charge. Now, if you have capacitors in parallel, that's a little different. So what does that mean? So if we were to look at this, here's my battery, it's positive. So the current's going to get here, and when it gets to this junction right here, some of the current's going to go into here, and some of the current's going to go into here. There's two different currents that are going in. There's two different paths. And so if you have more than one path of current, then that means that the capacitors are in parallel. It turns out that the voltage across V1 and V2 and V3 is going to be equal to the voltage of the battery, right? It's going to be the same. So they all have the same voltage, but that means that they have different charges. So Q1 is not going to be equal to Q2, is not going to be equal to Q3. So what that means is that the total charge of the circuit, because remember, this battery thinks that it is connected to just one equivalent capacitor. Its total charge is going to be equal to the sum of those charges of Q1 plus Q2 plus Q3. And remember that C equals Q all over V, so Q is equal to C times V1. So Q1 would be C1 times V, Q2 would be C2 times V, and Q3 would be C3 times V. And so it turns out that the equivalent capacitance of capacitors in parallel is just the sum of those. So the more capacitors that are in parallel, the more capacitance and the more charge that circuit can hold. So if we go back to our numbers, if this was 1 farad and this was 2 farads and this was 2 farads again, the equivalence would be 1 plus 2 plus 2, or 5 farads, versus our series combination that was only 0.5 farads. So you should be able to find the total capacitance of capacitors in series and in parallel. So here's an example. These are in series. So remember that the capacitance of capacitors in series is 1 over CEQ equals 1 over C1 plus 1 over C2 plus 1 over C3. How do I know they are in that they are in series? Because there's only one loop of current in this. There's only one loop of current, so this is the formula I'm going to use. 1 over 10 microfarads plus 1 over 2.5 microfarads plus 1 over 0.3 microfarads. So when I plug these in a calculator, I'm going to take 10 to the negative 1 plus 2.5 to the negative 1 plus 0.30 to the negative 1 to get whatever that is equal to. So 10 inverse plus 2.5 inverse plus 0.3 inverse equals, and that's going to be equal to 3.83 microfarad to the negative 1. And remember that in order to get CEQ, I'm going to need to take negative 1 of all of these, right? I'm going to need to take negative 1 of this. I'm going to have to take the inverse of that. So if I take the inverse of that, I'm going to get 0.261. So CEQ is 0.261 microfarads, or 0.261 e to the negative 6 farads. Oops. If I have a capacitor where they're all in parallel, so let's do an example like that. So let's say I have 10 microfarads. Actually, let me, let's say I have 10 microfarads, 2.5 microfarads, and 0.30 microfarads, and I want to find the equivalence of that. Remember, these are in parallel. How do I know? Because there's more than one loop of current in this, more than one pathway. So CEQ is just going to be the sum of those, 10 microfarads plus 2.5 microfarads plus 0.30 microfarads. So CEQ would be equal to 10 plus 2.5 is 12.5 plus 0.30 is 12.80 microfarads. If I wanted to know the total charge that these would hold, if I had a voltage of 120 volts applied to them, the charge, C equals Q all over V, the charge would be CEQ times the voltage across them, which would be 12.8 e to the negative 6 farads times 120 volts, 12.8 exponent negative 6 times 120. So this could hold a charge of 0.00154 coulombs. What if I have a more complicated one? So if I have a more complicated one, what I need to do is identify which ones are in parallel first, simplify it down, and then go from there. So when I look at this, these two are in parallel. So they are really acting like a branch. So you have the 1.5 microfarad is really acting like 0.75 plus 15, which is 15.75 microfarads. And it looks like these two are in series, and these two are in series. So if I want to find these two are acting like one capacitor, and that's connected to in the middle, and these two here are acting like one capacitor. So what I need to do is find the equivalence of these two. Well, they are in series. So 1 over C equals 1 over 5 plus 1 over 3.5. So 1 over plus 3.5 1 over equals 0.486, and take 1 over of that. I have to take the inverse of that, which is 2.06. So this is acting like 2.06 microfarads connected to an 8.0 microfarad. And these two right here, 1 over C is equal to 1 over 1.5 plus 1 over 15.75. And then I'm going to take the inverse of that. So 1.5, 1 over plus 15.75, 1 over equals, and take the inverse of that, 1.50 microfarads. So they're acting like, all of these are acting like 3 in parallel, and now I just add them together. So the equivalent for the whole thing is 2.06 microfarads plus 8 microfarads plus 1.5 microfarads. So 2.06 is 10.06. And it's 11, it's 12.1. So this is going to be 12.1 microfarads.